Okay, so this problem reads, a 100-gram toy car is propelled by a compressed spring that starts it moving. The car follows a curved track. Show that the final speed of the toy car is 0.687 meters per second if its initial speed, so after it is released from the spring, is 2 meters per second, and it coasts up a frictionless slope, gaining 0.18 meters in altitude. All right, so let's just identify what we're talking about, make sure we understand the picture. So here we have this car, and it is going to go up a curved track, and it's going to reach an altitude of 0.180 meters. And at this point on the track, we know that its speed is equal to 0.687 meters per second. At least that's what we're trying to decide. Is it equal to 6.8 meters per second? At this point, as it begins, after that compressed spring, as it goes up that track, we know that it has a speed of 2 meters per second at that point. All right, well, we can solve this problem using energy and the idea of conservation of energy. So what does that tell us? We want to remember that conservation of energy tells us that the total initial energy equals the total final energy. So the energy at one point in time, we'll call that initial, has to be the same as the energy at another point in time. So we want to define a couple of things about our problem. First, what defines initial and what defines final, so that we know what energy states to look at. In this case, it's going to help us if we recognize that that initial energy state isn't when the spring is compressed, because I don't have any information about the spring, but instead when it begins moving off the spring. So as it moves off at that 2 meters per second. So that's going to be our initial condition. And we'll look at the total energy at that point in time. Our final condition is when it reaches that peak, or the peak we're talking about, when it reaches the height of 0.180 meters. We know that's actually not a peak because it's moving. We're going to see if it's moving at that speed that we're predicting. All right, when we think about total energy, we want to think about what options do we have for energy. This is a mechanical energy example, so we have potential energies and kinetic energies. Now we have a spring involved, and that can have potential energy, and we have gravity involved in different heights, so that's a type of potential energy. Since we're looking after it moves off that spring, the spring's potential energy is not going to be a part of the picture. But we do want to consider the gravitational potential energy because we know that the car rises to a certain amount. And so in order for us to do that, we have to define where the zero value is. And we get to choose that to make it the most useful for our problem. So we're going to define the zero value at this bottom of the track. So this is going to be our height equal to 0 at that bottom of the track. All right, so let's look at our total energy relationship. We know that we have initial kinetic energy plus initial potential energy, and that's in the form of gravitational. And that's going to equal our final kinetic energy plus our final gravitational energy. Now, we know that it's starting at height equal to 0. So there's no potential energy as we have defined it initially in the situation. So we can take out that potential energy. And we're seeing does the initial kinetic energy equal the sum of our two types of energies in the final case. So we have initial kinetic energy of 1/2 mv initial squared. That's going to equal our final 1/2 mv final squared plus mg times the final height that we get to. Now, we're given the mass in this situation, but we do have mass in every term, and so the mass actually will divide out across all terms. We can't always do that, but in this case we can because the mass will divide out in all terms. We are given the mass, so we don't have to do that, but it's good to recognize when that's a possibility. So now we know that we have 1/2 2.00 squared is going to equal 1/2 V final. That's what we're interested in determining based on our question. Plus 9.8 times the height that it reaches above its starting point of 0.180 meters. All right, so 1/2 of 4 is 2, is going to equal to 1/2 V final squared. And I know you all can do this algebra. 9.8 times 0.18 is 1.764. If I bring 1.764 to the other side, I get 0.236 is equal to 1/2 V final squared. Solving for V final, we get 0.687 meters per second, which is what we were supposed to determine. Whoa, I'm off screen, aren't I? Let me move that. I didn't realize that I'm a little off screen today. I'll have to adjust my camera. Apologize for that. So when we do that, we get V final is equal to our 0.687 meters per second. And that's what we were supposed to compare it to. So using energy, really efficient process, recognizing the types of energy we have in the problem, identifying what those 2 time points are, initial, final, 1, 2, however you want to identify that. And then we need to recognize where it makes the most sense for us to put that height equal to 0. And it helps us to get rid of a term if we put that height equal to 0 at the start in this example. All right, good job.